Hello friends, welcome to my lecture on residue at a singularity. The behavior of singularities into poles and essential singularities is the classification of singularities into poles and essential singularities is not merely a formal matter, because the behavior of an analytic function in a neighborhood of an essential singularity is entirely different from that in the neighborhood of a pole. Let us see how is the nature of the function in the neighborhood of a pole. Suppose f z is analytic and has a pole at z equal to z naught, then mod of f z tends to infinity as z tends to z naught in any manner. That means, in a neighborhood of z equal to z naught, f z becomes indefinitely large. So, if f z has a pole of order m at z equal to z naught, then we can write f z like this, because if f z has a pole of order m at z equal to z naught, then by Laurent series f z is equal to sigma n equal to 0 to infinity b n z minus z naught to the power n plus sigma n is equal to 1 to m c n z minus z naught to the power minus n. Okay. So, this is so here this is nothing but z 1 over z minus z naught to the power m, and then we shall have sigma n equal to 0 to infinity b n z minus z naught to the power n plus m plus c 1 times z minus z naught to the power, we have here c 1 z minus z naught to the power minus 1. So, this will be equal to m minus 1, okay, c 2 z minus z naught to the power m minus 2 and so on, c m minus 1 z minus z naught plus c m. Okay. So, we can write like this, okay, if f z has a pole of order m at z equal to z naught. Now, this is equal to z minus z naught to the power minus m into phi z, and phi z is this Taylor series. You can see here, and when n is equal to 0, we have b naught z minus z naught to the power m here. So, we can start with this c m minus 1 z minus z naught, then c m minus 2 z minus z naught whole square, then c 1 z minus z naught to the power m minus 1, then the term in z minus z naught to the power m, which is b naught z minus z naught to the power m, then b 1 z minus z naught to the power m plus 1 and so on. So, this is the expression inside the square brackets is a Taylor series of some function which we denote by phi z. Now, phi z is also, you can see phi z is z naught is equal to c m, okay, which is non-zero, because f z has a pole of order m at z equal to z naught. So, phi z is analytic in mod of z minus z naught less than r, and phi z naught is equal to c m, where c m is non-zero. Now, we can take the limit of mod of f z as z tends to z naught, okay. Mod of f z is equal to mod of phi z over mod of z minus z naught to the power m. So, as z goes to z naught, phi z is a continuous function because it is analytic in this region. So, it is continuous. So, therefore, and also phi z is not equal to 0. So, as z tends to z naught, we can see that this expression mod of phi z over z minus z naught to the power m goes to infinity. So, when f z has a pole of order m in a neighborhood of f z, in a neighborhood of z equal to z naught, f z becomes arbitrarily large, okay, so indefinitely large. So, thus in a sufficiently small neighborhood of a pole of an analytic function, the absolute value of the function becomes indefinitely large. Now, suppose let us look at the limit point of zeros and poles. If f z is an analytic function in a domain D, and if z 1 z 2 is a sequence of zeros of f z in D having a limit point in the interior of D, then f z is identically 0 in D. So, let us consider that z naught be the limit point of the sequence of zeros z 1 z 2 and so on of f z, since z naught is the interior point of the domain D, okay, it follows that f z is continuous at z naught. Okay. F z is analytic inside D, and therefore, it is continuous inside D, and z naught is a point in the interior of D. So, f z is continuous at z naught, and therefore, f z naught must be 0. Now, let us see how f z naught is equal to 0. See, we have z 1, z 2 and so on. This is a sequence of zeros of f z. Okay, and z naught is the limit point of z 1, z 2 and so on, it is this sequence. Okay. Now, f z is continuous at z naught, implies that for a given epsilon greater than 0, there exists a positive number delta such that mod of f z minus f z naught is less than epsilon whenever mod of z minus z naught is less than delta. Okay. Now, for delta greater than 0, okay, for this delta greater than 0, we can find an integer n naught such that mod of zn minus z naught is less than delta for all n greater than or equal to n naught. Okay. So, what will happen? Mod of zn minus z naught is less than delta for all n greater than or equal to n naught. Let us combine the equation 1 and 2. Okay. From 1 and 2, we find that mod of f zn minus f z naught is less than epsilon, okay, for all n greater than or equal to n naught, because all these points zn for which n is greater than or equal to n naught, they are at a distance delta less than delta from z naught. And so, by the definition of continuity, mod of f zn minus f z naught is less than epsilon. This implies that mod of 0 minus f z naught is less than epsilon for all n greater than or equal to n naught. Okay. So, this will mean that mod of f z naught is less than epsilon. Okay. So, this means that f z naught is equal to 0, since epsilon greater than 0 is arbitrary. And thus we can say that because of the continuity of f z at z equal to z naught, and z naught being the limit point of the sequence of zeros at z 1, z 2 and so on, it follows that f z naught is equal to. So, this f z naught is equal to 0. Now, since z naught is a limit point of the sequence z 1, z 2 and so on, okay, every neighborhood of z naught, okay, howsoever small b take, will have infinitely many points of the sequence z 1, z 2 and so on. This implies that z equal to z naught, okay, is not an isolated 0 of f z, okay, it is not an isolated 0 of f z, and therefore, f z must be identically equal to 0. Okay. So, if f z is an analytic function and z 1, z 2, z n is a sequence of zeros, okay, having a limit point in the interior of D, then f z must be identically 0. Now, from the above theorem, it follows that the limit point of the sequence of zeros of a non-zero function, which is analytic in a domain D, cannot be an interior point of D. It is if it is an interior point of D, then f z must be identically 0. Okay. So, if the sequence of zeros of a non-zero analytic function is a singularity of f z, it is an isolated singularity. Now, this isolated singularity cannot be a pole, okay, because in the neighborhood of in any neighborhood of this singularity, okay, fz is not becoming indefinitely large. Every neighborhood of z equal to this singularity at z equal to say z naught, okay, we have infinitely many zeros of the function fz. Okay. So, since fz does not become indefinitely large in any neighborhood of this singularity at z equal to say z naught, okay, it follows that it is not a pole, and therefore, it must be an isolated essential singularity. So, to discard this case, okay, that it is not a pole, we are using this theorem, okay, because poles are isolated singularities. Okay. So, here we are finding an isolated singularity, but that isolated singularity cannot be a pole. Okay. If it is a pole, then in an arbitrarily small neighborhood of z equal to z naught, fz must tend to infinity as z tends to z naught. But here what do we notice? Howsoever small neighborhood of z naught we take, there are infinitely many zeros of the function fz, and therefore, fz tends to infinity is not possible. So, the singularity at z equal to z naught cannot be a pole, it must be an isolated essential singularity. So, this means that if the function fz, if the analytic function fz is non-zero, then the sequence of zeros of its zeros will always tend to a isolated essential singularity of the function. So, for example, let us consider this fz equal to sin 1 by z. It has zeros at z equal to 1 over n pi, where n takes values plus minus 1, plus minus 2 and so on. You can see sin 1 by z equal to 0 means 1 by z equal to n pi. Okay. So, where n takes values plus minus 1, plus minus 2 and so on. So, z equal to 1 over n pi, where n is equal to plus minus 1, plus minus 2 and so on. Now, if z equal, let us consider the sequence z equal to 1 over n pi. Okay. For this sequence, the limit point is z equal to 0. Okay. Now, since sin 1 by z, okay, sin 1 by z is a non-zero analytic function, therefore, z equal to 0 must be an isolated essential singularity of sin 1 by z. Now, let us go to Picard's theorem, which tells us the nature of an analytic function in a neighborhood of an isolated essential singularity. So, an analytic function fz having an isolated essential singularity at z equal to z naught assumes every value with at most one exceptional value in any arbitrary small neighborhood of z naught. So, it means that if fz has an isolated essential singularity at a point z equal to z naught, then it will assume every value except at the most one value, okay, in an arbitrarily small neighborhood of z naught. Let us illustrate this Picard's theorem for the function fz equal to e to the power 1 by z. We are going to show that this fz equal to e to power 1 by z, which has an isolated essential singularity at z equal to 0, assumes every value in an arbitrarily small neighborhood of z equal to 0 except just one value, and that value is z equal to 0. We can see that e to the power 1 by z is never 0 for any complex number z. To show that, let us consider fz, let us multiply e to the power 1 by z by e to the power 1 by z conjugate. Okay. Then this is e to the power 1 by z plus 1 by z conjugate, okay, which is equal to e to the power z plus z conjugate divided by z conjugate. Okay. And if z is equal to x plus iy, z conjugate will be x minus iy. So, this will be e to the power 2x divided by mod of z square. Z conjugate is mod of z square. So, this is x square plus y square. Okay. So, x square plus y square, and z is a non-zero complex number. So, this e to the power 2x over x square plus y square, this is a real function. Okay. 2x over x square plus y square is a real number. Okay. So, this is e to the power y, where y is 2 over 2x over x square plus y square, and e to the power y we know e to the power y is always greater than 0 for every y, okay, for every y belonging to R. Okay. So, e to the power z can e to the power, thus e to the power 1 by z can never be 0 for any z. For any complex number z, for any z not equal to 0. Okay. Now, let us show that it assumes every value, okay, in an arbitrary small neighborhood of z equal to 0, okay, except of course, can never be 0. Okay. Now, let us take let us say let z be equal to r e to the power I theta and c equal to c naught e to the power I alpha be any complex number. Okay. C equal to c naught e to the power I alpha, where c is not 0, okay, be any complex number. Then e to the power 1 by z is equal to e to the power 1 upon r e to the power I theta will be equal to e to the power 1 by r cos theta minus I sin theta. Okay. E to the power 1 by r into e to the power minus I theta is e to the power 1 by r cos theta minus I sin theta. Let us put it equal to c naught e to the power I alpha. Okay. This c naught e to the power I alpha. So, then equating the absolute values and arguments on both sides, you see we have absolute we have e to the power 1 by r cos theta, left side is e to the power 1 by r cos theta minus into e to the power minus I upon r sin theta equal to c naught e to the power I alpha. So, taking absolute values both sides, we find that e to the power 1 by r cos theta equal to c naught, and equating the arguments, what we get, alpha is equal to minus 1 by r sin theta. Okay. So, now this equation gives you e to the power 1 by r cos theta equal to c naught, e to the power 1 by r cos theta equal to c naught implies that 1 by r cos theta equal to ln c naught. Okay. And alpha equal to minus 1 by r sin theta gives you what, r we can say cos theta equal to r ln c naught, okay, and sin theta equal to minus alpha r. Okay. So, sin square plus cos theta, sin square theta plus cos square theta is equal to 1. So, we can say that r square alpha square plus r square ln c naught square is equal to 1. R we can say r square equal to 1 by ln c naught square plus alpha square. Okay. And tan theta is equal to minus alpha r over r c r ln c naught. So, tan theta is equal to minus alpha over ln c naught. Okay. Now, let us see r can this r is the modulus of z. Okay. This r can be made arbitrarily small by adding multiples of 2 pi to this alpha. Alpha is the argument of this complex number c, and by adding multiples of 2 pi to alpha, this c will remain unaltered. Okay. So, we notice that we obtain r square equal to 1 over ln c naught square plus alpha square and tan theta equal to minus alpha over ln c naught okay, where we have taken c equal to c naught e to the power I alpha. Okay. Now, what we notice here that r can be made arbitrarily small by adding multiples of integer multiples of 2 pi to alpha. Okay. So, we can replace alpha by alpha plus 2 m pi, okay, where m is an integer, okay, but that will not change the value of c. C will remain c naught e to the power I alpha plus minus 2 m pi if you take, okay, it will remain c naught e to the power I alpha. So, without changing the value of this is c. So, c equal to c naught e to the power I alpha again. So, without so c r can be made arbitrarily small by adding integer multiples of 2 pi to alpha, but c remains, leaving c unaltered. Okay. So, now what we have seen, you take any complex number c equal to c naught e to the power I alpha, where c is of course non-zero, okay. Then in an arbitrarily small neighborhood of z equal to 0, okay. See you this r z we have taken as r e to the power I theta, okay. So, in an arbitrarily small neighborhood of z equal to 0, because when you take and you add integer multiples of 2 pi to alpha, then this r will go on becoming small, okay. So, r can be made arbitrarily small by adding integer multiples of 2 pi to alpha, and this gives you a neighborhood of z equal to 0. So, in an arbitrarily small neighborhood of z, okay, equal to 0, e to the power 1 by z assumes is an arbitrary complex number, okay. This is an arbitrary complex number other than 0. Okay, now let us go to residue at a singularity. Let f z have an isolated singularity at a point z equal to z naught. Isolated singularity means you can find a neighborhood of z equal to z naught in which f z does not have any other singularity. Okay, so, then f z can be represented by a Laura series f z equal to sigma n equal to 0 to infinity b n z minus z naught to the power n plus sigma n equal to 1 to infinity c n over z minus z naught to the power n, which this series converges in a deleted neighborhood of z naught. So, if you have z naught point here, okay, you can then you can find a neighborhood of z naught, okay, which is a deleted neighborhood. Okay. R is the distance of z naught from the nearest singularity of f z. So, in this neighborhood f z can be represented by the Laura series given by this. Now, from the Laura series expansion we find that the coefficient C1 of 1 over z minus z naught is equal to 1 over 2 pi I integral over C f z dz, or we can say integral over C f z dz equal to 2 pi I C1. Let us recall that in the Laura series Cn's are given by 1 over 2 pi I integral over C f z dz divided by z minus z naught to the power minus n plus 1, okay, and taking values 1, 2, 3 and so on. Okay. So, here if you take n equal to 1, okay, here n equal taking n equal to 1, what do you get? 1 by 2 pi I C1, okay, gives you 1 over 2 pi I integral over C f z dz. Okay. So, when you take n equal to 1 here, you get the value of C1. This C1 is called the residue of f z at z equal to z naught. Residue of, and be denoted like this, residue of f z at z equal to z naught. Okay. This is the coefficient of 1 over z naught. You can see this is C1 over z minus z naught, like that. The coefficient of 1 over z minus z naught is C1 here. Okay. So, and this C is the simple closed curve. C is any simple closed curve which lies in the annular region, this one annular region, and encircles Z naught, that is Z naught lies in its interior. So, it can be taken any simple curve, closed curve like this, okay, which lies in the annular region 0 less than mod of Z minus Z naught less than R, and encircles the inner circle, point circle. So, we can say this is integral over C f z dz equal to 2 pi I C1, where the integration being taken in the counterclockwise sense around a simple closed path C, which lies in the region 0 less than mod of Z minus Z naught less than R, and contains the point Z equal to Z naught in its interior. The coefficient C1 in the development 1 of f z, in this development the coefficient of C1, the coefficient C1 is called the residue of f z at Z equal to Z naught, be denoted by residue of f z at Z equal to Z naught like this. Now, since Laurent series of f z can be obtained by different methods without using the integral formulas for the coefficients, you know we have the integral formulas for the coefficients Bn's and Cn's. For Cn we have this formula, and for Bn we have the formula 1 over 2 pi I integral over C f z dz divided by Z minus Z naught to the power n plus 1, where n is equal to 0 plus minus 1 plus minus 2 and so on. Okay. So, Laurent series of a function f z are obtained by different methods without using, rarely the formulas for the coefficients are used. Okay. We use alternate methods to find the Laurent series of f z in a given annular region. So, we obtain the Laurent series of the function f z by any alternate method, and then we determine the coefficient of 1 over Z minus Z naught in that, which gives us the value of C1. Then the integral of f z dz around the curve C is given by 2 pi I into C1. Okay. So, we can use that Laurent series to determine the contour integral. So, for example, let us consider this function integral over C f z square e to power 1 by Z dz. Here f z is equal to Z square e to the power 1 by Z, which we can write as Z square times, let us write the expansion of e to power 1 by Z. We know that e to the power Z is 1 plus Z square by 2 factorial, Z cube by 3 factorial and so on. So, replacing Z by 1 by Z, we get e to the power 1 by Z as 1 plus 1 by Z, 1 by 2 factorial Z square, 1 by 3 factorial Z cube and so on, which converges in the region 0 less than mod of Z less than infinity. So, here 1 plus 1 by Z, 1 by 2 factorial Z square, 1 by 3 factorial Z cube and so on, we get this. So, this is Z square plus Z plus 1 by 2 factorial, 1 by 3 factorial into Z, 1 by 4 factorial into Z square and so on we get. Okay. Now, this is the Laurent series of the function f z in the region 0 less than mod of Z less than infinity. Okay. Z equal to 0 is the only singularity of f z, and this is an essential singularity. You can see, because the principal part, this is the part which is sigma, this part is corresponding to sigma n equal to 0 to infinity b n z to the power n. Here we are taking z naught is equal to 0, and this part, okay, corresponds to sigma n equal to 1 to infinity c n z to the power minus n. Okay. So, the principal part contains infinitely many terms, and therefore, the singularity at z equal to 0 is an essential singularity. So, f z equal to z square e to power 1 by z has an isolated essential singularity at z equal to 0, and the coefficient of, now let us find the coefficient of 1 over z minus z naught. Z naught is 0 here. So, coefficient of 1 over z is equal to C1 equal to 1 by 3 factorial, which is 1 by 6. Okay. So, integral over C z square e to the power 1 by z dz will be equal to 2 pi I C1. Okay. So, 2 pi I by 6, and we get pi I by 3, okay, where the integral around C is being taken in the counterclockwise sense. Now, let us take one more example, say integral over C sin z over z to the power 4 dz. Okay. You can see that sin z over z to the power 4 can be expressed as 1 over z to the power 4, and we know the expansion of sin z, z minus z cube by 3 factorial, z 5 by 5 factorial, and so on. And this is therefore z over z cube, so 1 over z cube minus z upon 3 factorial, and then we have 1 over 3 factorial into z, okay, then 1 over 5 factorial into z, okay, and then we have minus 1 by 7 factorial into z to the power 3 and so on. Okay. Now, here you can see the principal part contains only finitely many terms. You see there are only 2 terms in the principal part, 1 over z cube minus 1 over 3 factorial z. Okay. So, since the principal part contains only finitely many terms, we have a pole at z equal to 0. We have a pole at z equal to 0 of order 3. We have minus 1 over 3 factorial into 1 over z plus 1 over z cube. So, it is of order 3. The coefficient of 1 by z is equal to minus 1 by 3 factorial, that is minus 1 by 6. So, this is the value of C1, okay, and therefore, the integral over C sin z over z to the power 4, okay, dz is equal to 2 pi I into C1, which is 2 pi I into minus 1 by 6, and this is minus pi I by 3. And you can notice that the region of convergence is 0 less than mod z less than infinity. Mod z equal to 1 is the circle, this one. This mod z equal to 1, okay. So, this is 0, okay. Mod z equal to 1 is the simple closed curve which lies in this region, okay, 0 less than mod z less than infinity, and contains the point z equal to 0 in its interior. Same is the case here in the previous example. The region of convergence is 0 less than mod z less than infinity, and mod z equal to 1 lies in this annular region and encircles the point z equal to 0, this point, this mod z equal to 1. Okay. So, this is how we can use the Laurent series to determine a contour integration. In our next lecture, we shall study the residue theorem, okay, which will be an extension of this case. Here we have only one singularity inside the simple closed path C, okay. So, this method will be extended to the case where the curve C contains a finite number of singularities inside it, okay, and then it is a very simple and elegant method to determine the contour integration in case the curve C has infinite number of isolated singularities inside it. So, with this I would like to end my lecture. Thank you very much for your attention.